in number theory. So I'm quite honored to be giving lectures in his name. It's a very old topic. It's a very huge topic. There's no way in a public lecture like this I can tell you everything that's going on. I don't even know everything that's going on. So I'm going to just give this very, very quick tour, the way I like to describe it. It's like visiting Paris and only seeing the Eiffel Tower and the Arc de Triomphe. You know, it's not really the full story, but it's something. Okay, so but it's about the prime numbers. And just to remind you, everyone, what a prime number is. A prime number is any natural number bigger than 1, which can't be factored into 2 smaller numbers. And so up there we have the first few prime numbers, and they just go on and on and on and on. The biggest one that we know of is down there. Okay, so we found a lot of primes. They've been studied for a long, long time. In fact, the ancient Greeks were the first people to study them systematically. In fact, Euclid, even Euclid in his Elements had several results on the prime numbers. And they proved the first 2 really important theorems about the primes. And that's a starting point for everything else. So the first thing we know about the primes is what's called the fundamental theorem of arithmetic. And it says that every natural number bigger than 1 might not be prime, but even if it's not prime, you can always factor it into primes. Every number is either prime or the product of primes, and there's only one way to write every number as a product of primes, other than rearranging. So 10 is 2 times 5, or 5 times 2, but that's the only way to split 10 into primes. That's the fundamental theorem of arithmetic. The other major theorem that they proved is called Euclid's theorem. So Euclid proved many theorems, but this is the Euclid's theorem, that the primes go on forever. There are infinitely many prime numbers. The primes never stop. Okay, so these are 2 basic theorems in Greek prime number theory. So the fundamental theorem that every number can be split up into primes, one way to think about it is what it tells you is that the prime numbers are very important to integer multiplication. They're like the atoms. If integers are like molecules, then prime numbers are like atoms. They're the atomic elements of integer multiplication. Every molecule is made up of atoms, carbon dioxide, CO2, and similarly, every integer is made up of primes in exactly one way. And so here are a couple of numbers and their prime factorizations. By the way, this is, by the way, the main reason why we don't consider 1 a prime number. So, of course, 1 has no factors other than itself. So you're saying, why don't we call 1 prime? Well, if we called 1 prime, then there'd be more than one way to split up a number into primes. Like the number 10 could be 2 times 5, but also 2 times 5 times 1, 2 times 5 times 1 times 1. And you wouldn't have a good, unique prime decomposition. And so you wouldn't have the fundamental theorem of arithmetic. And we really like the fundamental theorem of arithmetic. So we have demoted 1, and we do not consider it a prime anymore. Okay. So Euclid's theorem is a theorem that there are infinitely many primes. And I want to show you the proof of it because it's a beautiful proof. It's one of the first proofs in mathematics, but it's still a classic. It's a real gem. It's what's called a proof. It's a reductio ad absurdum proof, a proof by contradiction. You prove something is true by proving it is not false. It's an indirect argument. So I'll just show you how it works. So you want to prove that there are infinitely many primes. So you suppose there weren't. Okay, suppose that Euclid was wrong. Suppose there are only finitely many primes in the world, that after a while they just stop. So for the sake of argument, suppose that 2, 3, and 5 were prime, but then there are no further primes. Suppose that you can only find finitely many primes. Then what you can do is that you can take all those primes and multiply them together. So if 2, 3, and 5 are all the primes in the world, you multiply 2 times 3 times 5, you get 30. And then you add 1. You take the product of all these primes, you add 1 more, gives you a new number, in this case 31. Okay, so you take all the primes in the world, multiply them together, add 1, that gives you a new number. Now why do you do this? You do this because this new number is 31, is bigger than 1, clearly, and because it's 1 more than a multiple of all the primes in the world, it's not divisible by any prime. Okay, it's not divisible by 2, 3, or 5. It leaves a remainder of 1. Okay, so we have found a number which is bigger than 1, but it's not. It can't be divided into primes. But the fundamental theorem of arithmetic tells you that every number can be divided into primes. And so, because we know the fundamental theorem of arithmetic, we have reached a contradiction. So there can't be finitely many primes, and hence there must be infinitely many primes.